everyone, and welcome to your AP Physics 1 review session. This is number 3 of 3. A couple weeks back, a veteran instructor of ours, Will, gave us a nice review session talking about the new format of our test, the structure of it, how that was all going to work on test day. If you're curious about that aspect of your test, do check out Will's video that you can find on our Princeton Review YouTube channel. And then last week, I dove into some of the content, the equations and concepts that are commonly tested and that you're responsible for your test. And last week, I covered units 1 through 3, which brought us through kinematics, Newton's laws, as well as uniform circular motion and gravitation. What I'm going to do today is build on that by going through the other units. So we'll talk about energy, momentum, simple harmonic motion, as well as, based on time, torque and rotational motion. So my name is Dave McKenzie. I'm a veteran instructor with the Princeton Review. I've been working with this company since 2004, helping students hit their target scores on their tests, and hopefully I can help you along with that process here today. Physics is my thing. It's my background. It's what I've studied. It's what I've been working at, even before 2004. So needless to say, it's my jam. So go ahead and ask questions as they arise. Feel free to let me know whether it's about concepts of the physics or the specific examples. Happy to field your questions. So without further ado, let's dive in. So we're going to get into energy first. And that starts with a conversation on work. So what work is physically is it's a way of talking about the contribution that a force has on an object's displacement. And so it makes sense then that this quantity of work is defined in terms of those quantities of force and displacement. So we see here, work is the magnitude of your force in question onto the magnitude of the displacement experienced onto cosine of the angle between those two vectors. So although work is defined in terms of vectors, work itself is a scalar quantity. And as a scalar, this one could be positive, 0, or negative, depending on this angle theta, because cosine of theta could be positive, 0, or negative. So if we have a setup like we see here in this example, for this force here, this angle is an acute angle. So that would lead to a positive value of cosine for positive work. And physically, what this means is there's at least some part of your force or some component that goes with that sense of displacement to help it along. If we were to look at, say, other forces, like maybe the normal force in this instance, which is perpendicular to the displacement, that would end up giving us cosine of 90, which would lead to 0 work done. And again, that's reflective of what the components look like. The normal force doesn't have a component with the displacement, and it also doesn't have a component against the displacement. So it can't do positive or negative work, and therefore it does 0 work. And if we were to include something like, say, kinetic friction, we'll notice that the angle theta this time is the angle between our leftward kinetic friction and our rightward displacement, meaning 180 degrees, and cosine of 180 is -1, and so we find negative work done by this force. And again, physically what this represents is our force is acting against the motion, and that is a way of interpreting work physically here. So for an example where we can calculate work, we can look at example number 2. And in example 2, we have a 15 kilogram crate moved along a horizontal floor by a warehouse worker who's pulling on it with a rope that makes 30-degree angle with the horizontal. So the setup there is pretty similar to the previous picture, right? We've got a flat surface. There's some sort of a mass that'll experience this force, which is called a tension force in this case, as our object displaces to the right, and there's a known angle between those two. So the question here then gives us the tension in the rope is 69 newtons, and the crate slides a total distance of 10 meters, and we want to know the work done by the worker on the crate. So there's lots of forces here, meaning there's lots of works we could look for. So be careful with your question. What work does it actually care about? And here it looks like it wants the work from that tension force. So I'd say work is equal to force onto that displacement, onto cosine of that angle. So here we would have our value of tension onto the value of the displacement, and then cosine of 30 degrees. So cosine of 30 we could know is root 3 over 2. Or if you've got your calculator, go ahead and plug everything in here. And what you would find in this instance is about 600 with SI units of joules. And that is our unit for work. So this is a little look at what work is as a quantity, and what it gives us now is this way of wading into looking at physics with scalars, as opposed to what we did last time, which was all vectors, thinking about like force and acceleration. So now let's use work to get into a conversation on energy. It's a very powerful concept in physics, and how energy is defined is it's the ability to do work. So if an object can do work, we say it possesses this quantity of energy. So consider, say, a hammer moving towards a nail. Because the hammer is moving to the nail, it can eventually contact the nail. And as a result of the contact, deliver a force, which might push the nail or displace it into a wall. And there you get force and displacement together for a positive work done. So by virtue of the fact that the hammer was moving, we say it can do work and hence it must possess energy. So the energy associated with motion is what we call kinetic energy. And we see that here given by variable k. And we can calculate this as 1/2 the mass, which is a scalar, onto the square of the speed, which is also a scalar. So here we get another scalar to work with. This time it's based purely on other scalars, which is pretty nice. Because it avoids some of the complications that can come in with vectors, right? Where with vectors you had to worry about components, maybe some trigonometry, signs with the direction. And here we can kind of get around that, which is nice. So considering that definition of energy, how it's so intimately related to work, it would make sense that we should somehow be able to connect this kinetic energy to work. And that's what we see right here. The work kinetic energy theorem tells us that the net work or the total work done is equal to the change in the kinetic energy experienced. So if we look at example 6, we can see how some of this might be tested. So this example says, what is the kinetic energy of a ball, of known mass, moving with a speed of 30 meters per second? Well, to get that kinetic energy, we'll use our equation and plug in the pieces. So 1/2 mv squared, the mass is 0.1, our speed is 30, which we'll square. 30 squared is 900, times 0.1 is 90. Then we cut that in half to get 45 joules. So that answers example 6. What's kind of a neat extension to this that I can add on is maybe there could be a question that asks, well, what would the net work be by the force that got the object up to that speed if it started from rest? So let's add it in that note. If v initial was 0 meters per second, then what we can claim is the net work done by that force. And notice here, I don't know what that force is, right? But I can still find the work done because I can use this kinetic energy, work kinetic energy theorem to claim that the net work is the change in the kinetic energy, which would be our final kinetic energy minus the initial kinetic energy. And notice here, the initial kinetic energy is 0. After all, if we're not moving to begin with, if we're at rest, no motion means no kinetic energy. So this just goes to 0. And what I'm left with then is the value of the net work matches the kinetic energy in this instance, which was the 45 joules we just found. And the unit of kinetic energy is the same as the unit of work. And this equation helps to show that as well. But this isn't the only kind of energy there is. You can imagine, again, that hammer. If I hold it up and then I let go, it's going to fall, meaning it's going to acquire speed and it's going to start to move. So it's acquiring energy, which means now it can do work. So first off, by virtue of the position that it had, that height, now that hammer can do work. So there's also an energy associated with position. And that energy is what we call potential energy. And in the example that I'm bringing up with the hammer specifically, this is tied to gravity. So the potential energy due to gravity is kind of a neat one, right? Because gravity is what we call a conservative force. which by and large means it allows us to conserve energy, which we'll talk about shortly. And such forces have this nice relationship here, where the work done is equal to the negative of the change in its potential energy. So here's what we can claim. For this new quantity of potential energy that I'm bringing up, the change in that quantity should look like the work done. So for gravity, this should look like the force of gravity. So that's mg onto the displacement. And gravity causes those vertical displacements. So a change in height. Or if we wanted to, we can say, well, what would the potential energy be at just one point as opposed to how does it change? And the potential energy due to gravity at one position or one height would just be mg times that height value itself. And so where this often gets used, I kind of hinted at, this often gets used with conservation of energy. So total energy is kind of like total anything, right? Like last time we talked about net force. We find net force by adding up all the forces. To find the net work or the total work, we had to add up all the works. To find the net energy or the total energy, add up all the energies. So here we can say total energy is equal to the kinetic energy plus the potential energy. And if we've got conservation of mechanical energy, then we're saying this value for total energy is conserved. So whatever this total energy is, it's fixed, it's constant, it's not going to change. We can get changes in the kinetic and the potential energy, but they should still manage to sum to the same total energy. So one of the ways we could try to express that is like we see here. Add up the kinetic and the potential energy at some initial time. That should balance with the sum of the kinetic and the potential energies at some later time in some final state. So I see a question here. Sam says, this isn't an energy question, but I encountered an issue with static friction today. Why is it that kinetic friction always opposes motion, yet static friction sometimes acts in the direction of motion? Great question. I'm confused by static friction, how it can go in the direction of motion and kinetic friction can't. Yeah, no, fantastic question. Super counterintuitive stuff, right? Because you think friction's all about resistance, so it should go against the motion, right? Like that seems logical. But there are a number of examples you can come up with to see how this works. So for instance, think about the definition of static friction, right? It is a resistive force, yes, but it's one that says you've got two surfaces in contact, they're not moving against each other. Static friction says, let's keep it that way, right? So, for instance, if you thought about a fridge on the back of a pickup truck, for instance, as the pickup truck goes forward, if the fridge were to maintain its state of motion, which is initially stationary, then the truck would go forward, the fridge would stay where it is, and effectively it would slide off the back of the truck. Well, the bed of the truck says, I don't want that to happen. I don't want that sliding to start. So it exerts static friction to prevent the fridge from sliding off the back. And hence, it exerts static friction in a forward sense. And so it keeps the fridge moving with the truck. Same sort of thing with like a child sitting on a toboggan, right? You pull the toboggan and to make sure the child stays with the toboggan, the toboggan exerts a static friction force to prevent the child from sliding off the back. You can also think about walking as another case. Like every time you try to take a step, what you're doing is you're pushing backward on the ground. The ground says, don't slip against me. And it exerts static friction forward against your foot to prevent it slipping. So there you go forward with static friction that points forward. So there are a couple of cases in which that can happen. Can you let me know if that helps to clarify, Sam? So what we can do as an example with conservation of energy is now get into example number 12, which we see right here. And this says we have a ball of mass 2 kilograms gently pushed off the edge of a tabletop. This is 5 meters above the floor. And our question is to find the speed the ball has when it strikes the floor. So notice in the question, we want to find a final speed. We know it's basically starting from rest because it's pushed gently. And there's this change in height. So changes in speeds coming from changes in heights. The object is in free fall, right? Just gravity. Energy is conserved. Let's go there. And it can help here too to draw out the situation. So we've got this known height to fall from. Our initial speed is 0. You're welcome, Sam. There's this final speed we're looking for. And if energy is conserved, we can write that the sum of the initial forms of energy should balance with the sum of the later forms of energy. We can simplify this from the beginning, which is nice because having 4 terms to have to juggle can be a bit awkward. But so take a step back, right? Again, if the object has 0 speed to start, then it has 0 kinetic energy to start too. So that's going to start from rest. And if we say the ground is height 0, well, then our final potential energy would be 0. And what we're left with is this very classic case of one form of energy being converted completely into another. Here we've got potential energy due to gravity, mg height initial, being converted into kinetic energy later on, 1/2 mv squared. And notice, like, we know the mass in the question. They told us it's 2 kilograms, but we don't need it, right? It's the same on both sides, so we can divide it out, which kind of goes back to what I mentioned in our session last week, which was even when you're doing a computation problem, still go through the algebra, rearrange and isolate for the thing that you want. Sometimes that's the exercise, right? Come up with the expression. So you should get used to doing that. But B, if you plug in numbers right away, we'd have more numbers to handle, which would make the math a little bit more cumbersome, right? Which could lead to little errors. So simplify it first, set it up, isolate for what you want. Here to get V alone, we can double both sides, and then we can take a square root on both sides. So here we'd have the square root of 2 on to 10 on to 5, which gets us the square root of 100, which is 10 in SI units of meters per second. So this is a pretty classic kind of conservation of energy problem. You set it up the way we did, work the algebra, simplify and solve. Now we could have some complication here, right? Like in this instance, this is what we needed to set up and do because we only had gravity acting. It's a conservative force. We can dive in. But it's possible that we have forces that are non-conservative, forces that say and total energy won't stay constant. And one classic example of that is like kinetic friction, right? That's a force that takes energy out of the system, leaving you with less later on. So energy is technically not conserved, but that doesn't mean we have to like forget about energy considerations entirely. We can still use energy to solve those kinds of problems so long as we're careful to account for where the energy imbalance comes from. So to get a sense of that, look here. Here's the initial energy of our system, which if we think about, again, going to the example of kinetic friction, would be some big number. And then kinetic friction takes energy out. So here's our final energy, which would be some smaller value. Well, if we add in the work that kinetic friction does on the left-hand side of the equation, which is a negative value of work, like we touched on briefly earlier, um, then that can account for the mismatch, right? Because we'll have this big number adding on this negative quantity to give me the correct smaller value in the end. So if we do have a non-conservative force, add in its work on the left-hand side and everything will work out. So for example, 15, we have Wile E. Coyote with a known mass falling off a 50-meter high cliff. On the way down, the force of air resistance, which is like a kinetic friction, has an average strength of 100 newtons. Now we want to find the speed with which he crashes into the ground. So not too different than the example we just did, right? Like we could draw this out and we'd have a pretty similar looking picture. Right, so here's Wile E. Coyote approximated as a dot. Starting from rest, we'll get to the ground, have a certain velocity or a certain speed there, really, that we're interested in. We know the height through which he'll fall. But now there's this drag force, this air resistance, which is like a kinetic friction. So we'll still work this with energy, but now we'll be careful to include that work done by that air resistance, which maybe we call D for drag. And if we want to think about, well, how do I incorporate that? How do I find that work? We know the work is related to the forces that are involved, right? So let's draw in the forces. There's a gravity force, which we account for with the potential energy terms. And then there's this drag force, which is an air resistance. So it goes against the displacement. And now when we draw out the vectors, what we can see is literally just that the drag goes against the displacement, right? Drag is up, displacement's down. They're 180 degrees different from each other. This is an example, just like kinetic friction, where we're going to have negative work done. So let's simplify some of what we have here in our energy equation. So again, we're starting from rest, so there's no kinetic energy. We get to the ground where height can be 0, so that'll go away. And then we can plug in some pieces here. So the potential energy will be mg onto the initial height. The work done by the drag will be the drag force onto the displacement. And like we reasoned out, this is going to be a negative quantity. And that'll go to 1/2 mass speed squared. I see your question, Sam. I'll get back to that in just a second. So again, isolate for the thing we're looking for, which is the speed here. So take your time, do whatever steps you need to do to be very careful in getting the final expression. But certainly what we're going to need to do is double both sides and divide through by mass. And then take a square root. And what's interesting about this expression is notice what we have for our speed is it's root 2gh first and foremost, and that's what we had before. So if the drag force was 0, we'd end up with the same result we had last time. And when we do have a drag force, though, notice that we're subtracting some quantity, meaning our final speed now is going to be less than it would have been without the drag. And that makes sense because we're expecting this to slow us down. And now, again, like if you put in the numbers, you take your time working through the calculation, you should find that this ends up being about 27 meters per second in this case. So Sam says, in QQT and AP style problems, what situations are mostly like best to use for energy? Well, okay, so in terms of, how should I know to use what tools? Newton's laws, kinematics, energy, momentum, that kind of thing. Just think about what's happening in your question, right? Always, whenever you've got a question, first and foremost, keep your eye on the prize. Ask yourself, what am I looking for? Here's the speed. And then say to yourself, well, what am I given to help work this problem? And what I have in this instance is this change in height. I know an earlier speed. All of those things are tied into conservation of energy. And considering that we're falling, that gives us a sense of gravity, which would lead to conservation of energy. One little quirk to this problem is this drag force that we have to account for, but I can still deal with energy in this case. So think about it that way for any given problem, right? What are you asked for? What are you given? And what connects those pieces together? So pretty common tools to use for working problems include the kinematics big five, right? If you have constant acceleration, they can apply. If you're dealing with forces, think F net is ma. Draw a free body diagram, maybe work it that way. Like we'll talk about shortly, there's some red flags to use conservation of momentum, right? Collisions, explosion, recoil. And then energy is pretty powerful, pretty versatile. You can use it in a lot of scenarios like we're showing here. But it ultimately comes down to, what am I asked for and what am I given to help, and what relationships can I come up with that bridge those together? So hopefully that addresses your question, Sam. Okay, so this takes me through a little bit about what I wanted to cover in terms of energy. What I think I'll switch to now is momentum. So momentum is another way of trying to describe the motion of a mass, right? We've looked at a number of key things now to describe its motion. But for momentum, what we have is a vector quantity that's related to the velocity. So it gives us a sense of what our object is doing in terms of its motion. And for the mass, this gives us a sense of maybe its resistance to changing that motion. And this is what momentum tends to hint at. Let me just go back for a sec. It's coming to me that I need to, when I said double everything, actually double everything. So there's a factor of 2 on this term, and then I need to put the factor of 2 on here as well. So there we are. And again, like when you plug in, take all the steps you need to make sure that you get everything arranged correctly. Certainly on a test, you show a few more lines of work. And then when you plug in the numbers here, we should still recover that 27 meters per second. Sorry, going back to momentum, we get this quantity called p vector, which is m onto v vector. And given the description about how like momentum ties into the motion of our mass, and it gives us a sense of maybe a resistance to a change in motion, that sounds a whole lot like the discussion of force. So it shouldn't be surprising when we can find out that we can relate momentum back to force. And in particular, we find that force is equal to the rate of change of momentum. So there's a few definitions, a few equations to put down on your cheat sheets. How this is often tested for the AP Physics 1 test is through conservation of momentum. So in conservation of momentum, what we have is the following. So long as there aren't any unbalanced external forces, momentum is a conserved quantity. So you can have external forces on your system, they just need to balance out for momentum to be conserved. So if you thought about like, you know, two air hockey pucks sliding towards each other, for instance, they each feel a weight downward, but the table gives them a normal force upwards. So external forces, but they balance. So with no net external force, we can claim momentum's conserved. So just like we said for energy, the initial value should match a final value. It's the same thing here for momentum. If momentum is conserved, then the total initial momentum of your system should equal the total final momentum of your system. So like I said, there are a few places where this is often tested, and let's put those down. We'll make that little note here. This is often tested with the following: collisions in particular, explosions, recoil, and even radioactive decay. So certainly for your test, though, collisions, and you'll see this if you go back through the past exams that the College Board publishes on their website. You'll see like collisions really common when we see momentum being tested. But there's some red flags, right? If we see something like this happening within a question, we can think about using conservation momentum. So, Irish, you say, I have the Princeton Review AP Physics exam book, so I was just wondering that while I'm prepping, should I only be doing the free response questions since those are the only types of questions that will appear on the test? Great question. Let me say a few things about that. So first off, you should definitely be doing those kinds of problems because like you point out, those are the two questions you get are both free response questions. So you want to get used to working through that many steps, spending that much time on a problem, knowing how to present your work in that case, being very familiar with how those questions are often asked. So yes, devote, I'd say, more of your time to those questions, but I wouldn't suggest only doing those problems. Um, the multiple choice questions, which are no longer tested, but the multiple choice practice questions we have in our book, and for those of you at home perhaps wondering what this book looks like, here's a 2020 edition of our AP Physics 1 exam book. Highly recommended, no bias. But what you should also be doing is those multiple choice. And I say that because they give you pretty nice insights into a lot of the foundational concepts. They help show you the kinds of equations that are commonly tested. So it could be a good reminder like, oh, I need to put that on my cheat sheet, right? I didn't have that down. And they also give you a way that you can see like maybe a part of a free response question asked. So there won't be answer choices with the free response problem, but those questions that are in the multiple choice practice, they give you nice insights. They do present value to you while you study. But like I said at first, you definitely want to put most of your time to the free response questions. So hopefully that addresses your question. You can let me know either way. So momentum, conserved quantity, collisions, very common to see on our test. So let's talk a little bit about specific kinds of collisions, because it turns out we have three kinds of collisions we can focus on or be asked about. So imagine you've got two masses coming towards each other, like maybe the two air hockey pucks, right? One of the ways it could collide is in an elastic collision. And kind of like the word elastic suggests or hints at, this means there's perfect rebound, right? So the objects bounce perfectly off each other and they go off in various different directions. In this case, momentum is conserved, like I was saying in the previous slide, but also kinetic energy is conserved. And that's unique to this kind of collision, which is an important detail to bear in mind. If we had an inelastic collision, that in basically means not. So we've got a not elastic collision. So there is no perfect rebound. So here the two objects collide, and then they might head off in the same direction where one object kind of bullies the other one and wins out. So here momentum is conserved because it's a collision, but now kinetic energy is lost, right? And that can happen in a number of forms, right? When two objects actually collide in reality, I don't know if we can hear that on the mic or not, but they generate sound, and that takes energy out of the system. If they rub up against each other in the collision, that generates heat, and that takes energy out of the system. If there's deformation, like crumpling bumpers of cars that bump up against each other, that takes energy too. So there's lots of sources of energy loss in collisions. Um, and so in those scenarios, we'd have what's called an inelastic collision. And then this third case is actually an extreme form of that second scenario of an inelastic collision. And we call this one, oh, you're welcome, Narish. We call this one a perfectly inelastic collision. So perfectly meaning completely or totally no rebound. So in other words, the two objects collide and then they stick together and move off as one larger mass now, as we're trying to show here. So momentum is conserved, will be for all of our collisions, but we've got now the greatest kinetic energy loss in the scenario. So notice in working our problems, like we've got boxed off down here, if we're using conservation of momentum, we need to add up all of the momenta of all the objects in our system before and after. Hence, we've got two terms, right? For mass one and for mass two initially, and then two terms on the right. Mass one and mass two in the final case. And whether it's elastic or inelastic, it looks pretty similar, but where it's perfectly inelastic, if the two objects stick together, they travel with a common velocity afterward. And again, it's basically like one object with the total combined mass. So you can put those two terms together on the right-hand side, literally together. So with that said, let's get into an example to show you how to work these kinds of problems. That starts here with question 6. That says, two balls roll towards each other. We have a red ball with a mass of 0.5 kilograms and a speed of 4 meters per second just before the impact. The green ball has a mass of 0.2 kilograms and a speed of 2 meters per second. After the head-on collision, the red ball continues forward. So it maintains that same direction of motion, right? But now with 2 meters per second, so it's slowed down a bit. First off, find the speed of the green ball after the collision, and then address the question, was the collision elastic or not? So kind of like I was saying before with the energy problems, and also last week when it comes to projectiles or forces, like drawing out the figure can be very insightful, can be very helpful in terms of getting you to set up the problem and solve it, but also it's helpful to show the greater your understanding of the problem as well. So here we've got like a before and after scenario, right? Before the collision, after the collision. So let's draw that out. And before our collision, what we have is a red ball traveling forward with a certain speed. But then we also have a green ball heading towards our red ball with a certain speed. And then after the collision, what we're told is the red ball keeps going the way it was going, but with a new speed. So we'll call that V red final. And then the green ball is going to do something else. Now you can imagine if the red ball is able to keep going forward, it probably won out and bullied the green ball. So the green ball, you imagine, would also be heading to the right. But we can verify that by going through the math. So I see Sam has a question. It says, what would the ranking be for the final velocities of these collisions, such as highest to lowest final velocity? Oh, I see what you're saying. I would let each question work out what the velocities were, and I wouldn't try to worry about like any kind of generalized sense of like final velocities for certain masses, because again, you've got multiple masses that can be colliding in multiple ways. So so just know like when you've got collisions, we can work things out in terms of like what velocities there might be for the different masses afterward by working through conservation of momentum. And if you have an elastic collision, potentially you can also bring in conservation of kinetic energy. So I hope that satisfies your question, Sam. But having it set up this way, to find the speed of our green ball after the collision, we'll use conservation of momentum. So we can say our initial momentum is supposed to balance with the final momentum. And again, you have to add up all of the momenta of all the masses in each of those scenarios. So we would have the mass of the red ball onto the velocity of the red ball. And here you do need to be careful. These V's are velocities, meaning we have to worry about the direction of these vectors. So what you could do for yourself is with your figure, make a note. Where's your positive direction? And let's say to the right, or the way I've got it set up with the red ball, is the positive direction. So now I can say, well, this velocity has this speed or magnitude of VR, but in the positive sense. And then for the green ball, I would say I've got mass green onto V green as a magnitude, but it's in our negative sense. So I need to slap on this minus sign here. After the collision, the red ball continues in that forward or positive sense. And then for the green ball, we have the sense it should probably go to the right, with the red ball winning out. But you can always just, again, like let the math verify that for you. So we can add on mass green, um, the green final, and leave this as a vector where we're not too worried about the signs. If we end up pumping out a negative number, I guess it managed to go through the red ball the other way. Um, but but you can always just leave it as a vector and let the signs determine the direction after the collision too. So again, let's isolate for the thing that we want. So for V green final, the the left hand side, that's going to be still MRVR minus MGVG. We're not going to do anything to those terms. But this red final term, we're going to bring that over to the left hand side. So we'll subtract that as well. And then we can divide through by the mass of the green ball. So now we plug in the numbers and work the math. So for the red ball, it has a mass of 0.5 kilograms. Initially, the speed was 4 meters per second. The green ball has a mass of 0.2, initially traveling at a speed of 2 meters per second. Then our red ball, in the final case, continued forward with 2 meters per second. And we'll divide through by the green ball's mass, which was 0.2 kilograms. So now notice when working the math at this point, I'll have basically half of 4, which is 2. 0.2 onto 2 is 0.4. So I subtract that away to get 1.6. And then half of 2 is 1, which I'll subtract away. And that's going to leave me with 0.6. So I've got 0.6 divided by 0.2, but that's the same as 6 divided by 2. So in the end, I can find that this final velocity for the green ball is positive 3 with those SI units of meters per second. So notice that the velocity ended up being positive, which means the way we have it set up, to the right or with the direction of the red ball, as we anticipated, and we drew it out that way. But it's nice to see that the equations can and the math can verify that for us as well. And then it has a value of 3 with those units of meters per second. And always when you're writing out numerical results, like be sure to include those units. So that takes care of the first part of our problem, finding what that speed was for the green ball after the collision, 3 meters per second. But now we need to address the question, was the collision elastic? And like I said, what's unique about elastic collisions is the fact that under those cases, kinetic energy will be conserved. So if you want to see, is my collision elastic or not, compare the kinetic energies. So let's do just that. The initial kinetic energy comes from the contribution from the red ball plus the contribution from the green ball. We've got values for this. So plug in all those numbers. And here's what we come up with. 4 squared is 16. Cut in half is 8. Cut in half again is 4. And 2 squared is 4. Cut in half is 2. Times 0.2 is 0.4. And so we find 4.4 joules of kinetic energy to start. Going to life after the collision, we'd have half the red mass onto its new speed squared, and plus 1/2 the mass of our green ball onto its new speed squared. And again, now we've got numbers for all this. So the masses didn't change, but we do have new speeds. We'll have 2 meters per second for the red ball after the collision. And for the green ball, we just found 3 meters per second for the speed after the collision. So here, 2 squared is 4, cut in half is 2, cut in half is 1. And then 3 squared is 9, cut in half is 4.5, times 0.2 gets us an extra 0.9. And so we find 1.9 joules. So as an answer to the question, was the collision elastic? We would have to say no, because that initial kinetic energy does not match that final kinetic energy. So this was an example of an inelastic collision. It wasn't elastic because the kinetic energies didn't match, but it's also not perfectly inelastic because the masses do separate, right? This one goes off at 3 meters per second, while the red one only continues forward with 2 meters per second. So they are separate. So this is how we work momentum problems. And again, collisions in particular are very common with AP Physics 1. And you don't need to take my word for that. Again, go back through the past tests that the College Board publishes on their AP Physics website, and you can see that this is a pretty consistent theme. And this takes us through what I wanted to cover for collisions and momentum. So now what we can switch over to is a discussion of simple harmonic motion. And with simple harmonic motion, let's describe what that means. We've got movement that is repeating. That's what the harmonic part means. And then the simple part, ironically enough, is probably the most complicated part of the definition, because the simple part means the period, or equivalently frequency, of the motion is independent of amplitude. But that's what's kind of buried in with that term of simple. So so that's what we have: repeating, back and forth motion. Somehow the object keeps going back to where it was before, and in such a way that the period is independent of amplitude. So we're going to have to describe that in more detail and define some terms for you. So let's do so by looking at a very common kind of simple harmonic system, like the spring mass system we see here on the slide. So here's a mass. It's a block. It's attached to a certain spring that we see here. And the spring has a certain length, right? It's a solid object. That's how long it wants to be. But if we give this mass some energy, like we hit it or something, it can move. And as a result, it can deform the spring. The spring doesn't want to be deformed, right? It has a certain length that it wants to have. So what happens is if we move away from this rest position or equilibrium position, and we make the mass, say, move off to the right, it's going to start to stretch the spring. Well, the spring won't want that to happen. It'll exert a force to bring the mass back to equilibrium. So our mass will slow down and eventually stop. And at this maximum displacement from equilibrium, we say the mass is achieved in amplitude. But that spring is going to say, no, you got to keep coming back. Don't just stop, come back here. So it exerts a force on the mass to continue bringing it back. And it does literally that. It exerts a force, meaning the mass is accelerated or continues to speed up on the way back. So the mass gets back to where the spring wants it to be, but the mass has all this speed or momentum, and it's going to carry it through the rest position. So now the mass ends up compressing the spring like we see here, in which case the spring says, okay, no, don't do that either, exerts the restoring force back the other way. So eventually the mass stops at an amplitude now on the other side of the rest position, and then the spring pushes it back towards the rest position. But again, it's going to speed up, right? The mass will speed up that whole time. So it gets here and it's going to cruise through there, and the whole process repeats. And hence we get harmonic or repeating motion. So in particular for this spring mass system, we have what's called Hooke's law to give us what that restoring force looks like from the spring. So the force vector we see here is proportional to the displacement x. So that's how much of an extension or a compression the spring feels. and it's proportional to that, and it's also oppositely directed. So when the spring heads to the right, the force is to the left, and when the spring heads to the left, the force is to the right. So one example we could take a look at is example number 1 below here. And this says a 12-centimeter long spring, so that's how long it wants to be, has a force constant K of 400 newtons per meter. That is our set of units for K. Our question is, how much force is required to stretch a spring to a length of 14 centimeters? So we're after a force, we see a spring, we see K's and X's or distances of some kind involved. So we want to be thinking about Hooke's law. The thing to be careful with, though, as you can see here, we have a number of like length values, right? The 12 centimeters, the 14 centimeters. So we need to be very clear about what we want to use when it comes to the X in this equation. Remember, this is your displacement away from the rest position. So if the spring wants to be 12 centimeters long, well, at that length, the mass would be at the rest position. So if the spring is stretched to 14 centimeters, then the mass displaced through 2 centimeters. And so in this question, to get the magnitude of that spring force, we would do K onto X. K is 400. X is 2 centimeters. Again, watch those units, right? So this would be more like 0.02 meters. And this will work out to get us 8 with SI units of newtons. So Sam, I see your question. You say, do you think it's doable to self-study AP Physics C mechanics while taking AP Calculus BC? This is after I finished the AP Physics 1 course. Okay. Well, yeah, so the AP Physics C course has a lot of the concepts and equations and ideas taken from AP Physics 1, the mechanics content of it, but it layers on calculus, right? So it's always good to have had the exposure to the calculus first, learn the math first to then use as a tool when working that kind of precise physics. You could do them in tandem, and sometimes that's the experience you'll have in university if you go on to study physics. But it'll present you with a bit of a steeper learning curve because now you're kind of picking up both at the same time. So hopefully that addresses your question. So this is a look at our spring force, but now we again have some terms to continue to define. So like I pointed out when we first looked at simple harmonic motion a few slides back, amplitude is that maximum displacement from equilibrium. And we can have that happen on either side, right, to the right or to the left. But do notice they represent now extreme points in the motion, which make them interesting. Right? So at the amplitudes, we have maximum displacement. Well, the spring force was proportional to displacement, so it will maximize as well. And through Newton's second law, if F is really big, so is the acceleration. So we get maximum acceleration at either amplitude. And then you have the complete opposite through equilibrium. Zero displacement gets you zero force and hence zero acceleration. So this is a nice slide that brings you in some of those ideas. Spring force, much like gravity, is a conservative force. So there's a potential energy associated with it. And we see that here. This potential energy is given by 1/2 the spring constant K onto the displacement squared. So 1/2 kx squared. And now this quantity also has a dependence on position. So it would also be maximized at amplitude and go to 0 through equilibrium. And then considering it's conservative, it'll trade off perfectly with kinetic energy. So if we have a maximum potential energy, we should have a minimum kinetic energy. So kinetic energy and hence speed are going to be 0 at either amplitude, but through the equilibrium position where potential energy goes to 0, kinetic energy will maximize and so will the speed. So a question that can bring in energy considerations is example 2. It says we have a block of known mass oscillating on a spring whose force constant K is known. The amplitude of the oscillations is also known, and we want to find the maximum speed of our block. So it looks like they're giving me information about position when they bring up amplitude, and they're after speed. Well, those are the clues that we mentioned before with gravity to make us think of conservation of energy. So let's use it. And remember, conservation of energy says total energy is some fixed number, right? Won't change. So if you looked at any 2 points in the motion, the total energy should be the same. So let's set that up by looking at our extreme points. So we can say the energy, total energy at x is equal to, say, the amplitude, should be the same value as the total energy at x is the equilibrium position. And at amplitude, like we saw in the previous slide, all of the energy is potential energy. So this would be 1/2 k amplitude squared. But going through the equilibrium position, there is no potential energy. All of the energy is kinetic. And so here we would have 1/2 mass onto that maximum speed squared. So we can cancel out the 1/2 that are the same on both sides. And then we can rearrange this to get V max is the square root of k over m onto the amplitude, which is kind of a neat little equation that wouldn't be the worst to throw on your cheat sheet as well, where you can make a note for a spring mass oscillator. This is what the max speed is, and it goes through the equilibrium position. But certainly once we come up with the expression, we can plug in some numbers. So here k is 500, our mass is 0.05, and again, watch the units. The amplitude is 4 centimeters, or 0.04, putting it into SI units of meters. So 500 over 0.05 goes to 10,000, the square root of which is 100 times 0.04 gets us V max of 4 meters per second. So that brings us through thinking about energy for simple harmonic motion systems. But I still haven't defined what period and frequency are. So let's say a few words about those. So period is the special amount of time it takes for a full oscillation or a full cycle to occur. So number of seconds per cycle. Frequency, on the other hand, is how frequent the oscillations are, meaning it's the number of cycles that occur per second. And when we think about that definition and we look at those units that we can see here, it's no surprise then that these quantities are reciprocals. So period is 1 over the frequency, and frequency is 1 over the period. If we take a look at um, our spring mass system, it has a unique expression for the period and the frequency. And that's true for any simple harmonic motion system. It'll have its own equation for period and hence frequency. So here we've got period is 2 pi root m over k. And then if you wanted the frequency, flip it. 1 over 2 pi root k over m instead. And notice that these quantities of period and frequency depend on the properties of your system. So K, that restoring spring, right, that spring constant, and then M, the mass that's actually moving. So a question that brings this in is number 7, which would have us use the equations, insert the values, and solve. And when we use the equations that we can see above here on the slide, we should be able to recover that our period is 0.51. And note, when we go forward from there and we try to find a frequency, we don't need to put all of the same numbers back into here and then crunch all of that and solve. Because remember, um, frequency is the inverse of period. So what you could do is just take the reciprocal of your result, and this should churn out 1.9 with units of inverse seconds, which we often call Hz for Hertz. And then finally, I can also give us this nice summary of what's happening at those extreme points. And this wouldn't be the worst idea to put onto your cheat sheet as well, in case you get some conceptual questions tied into a freestanding, a free response question that you can see on your test. So here, this table, it summarizes the different pieces, and it makes sense when we consider the relationship with position. So for restoring force, we know its magnitude is directly proportional to the displacement. For acceleration, we know that's directly proportional to the force. And for spring potential energy, that's also related to position. So it makes sense when position is maximized, so are those quantities. And then through conservation of energy, we get the opposite for the kinetic energy. And because kinetic energy is tied into speed, we get the opposite for speed as well. So there are other kinds of common simple harmonic motion systems besides the spring mass system. For instance, a simple pendulum is one you could take a look at. But what's interesting is these sorts of concepts, where the restoring force is maximized, where the speed is maximized, where these things go to zero. That's a consistent story for what we see here. What I want to do, though, in the final few minutes of our time together is say a little bit about rotational motion. So we'll switch over and say a few things about that final unit. And one of the things that we can take away from rotational motion is that there are a lot of parallels to draw with linear motion or translational motion that we talked about last time. For instance, if we have constant acceleration, in this case, constant acceleration in terms of how fast we're spinning up or spinning in a slowing down kind of sense, as long as we have that constant acceleration, the big five still apply. But now what we're going to do is we're going to change the variables from the sort of alphabet that might be a bit more familiar to us, and we'll change it to this curvy Greek alphabet. So for the displacement, you think about the motion, it's going to be like counterclockwise or clockwise, right? So the motion is really like the angle that gets swept out when you're rotating. So the displacement here could be delta theta. For the speeds, we'll use omega, and for the accelerations, we'll use alpha. But otherwise, the equations are the same, right? There's nothing really different there. And that motion that we would earn, that kind of kinematics, is going to still owe its existence to force. But where force acts in a linear sense, something else must be at play to go from a linear action to like a rotational kind of motion. And this is where torque comes into play. So torque is sort of your rotational equivalent, I guess, or analog to force, right? It's the action that leads to rotation. So it involves the force in question, some sort of push or pull on an object, but it incorporates the specific geometry of the object. So r vector and sine of an angle between those two. So to define those terms, imagine you've got a door, right? Maybe this is a door as seen from above. So right here is the hinge of the door, which is the point about which the door would be rotating. And now let's imagine we push on the door with a force, say, acted in this manner. The r vector we're going to need, whose magnitude we'll put into that equation for torque, directly connects that hinge to where your force is applied. And then the angle theta is the angle that exists between those two vectors. So when you account for the actual shape and the geometry of the system and where it's pivoted or where it's going to rotate about, you can see how a force can then lead to some kind of rotation. And we model that with this quantity of torque. And because of that, torque leads to that change in motion. It's not too surprising then to learn that there is a sort of Newton's second law equivalent for rotation, right? So we can make the note that this is similar to what we had before with F net is ma. So that rotational action leads to a proportional rotational acceleration. And this I here is kind of like mass, right? Where mass was inertia or that resistance to a change in motion. Here, it's a resistance to a change in rotational motion. So this is called the rotational inertia. And we make the note here that it also depends on the mass. So the more massive, the bigger the I value there. But it also depends on how the mass is distributed. The farther away the masses are from the axis of rotation, or the point about which your system spins, the greater that value of I. So comparing these barbells down below, if these two have the same mass, the fact that the weights over here are far away from the point about which the spinning is occurring, or the axis of rotation, tells us that this will lead to a greater I value. And in the case over here, where those same masses are perhaps closer to that axis of rotation, we should anticipate a lesser value for the moment of inertia. And then finally, one last comment is about drawing analogies to momentum. So there's also angular momentum as well to consider. And angular momentum looks like inertia onto velocity, similar to what we saw with linear momentum. P is m onto v, inertia onto velocity. Same sort of thing found here. And in terms of the change in angular momentum and how we relate that to torque, that's similar to how we said force is a change in linear momentum over change in time, right? So change in momentum is that action onto time. Change in momentum is that kind of action onto time. So very, very self-consistent. So when you can draw those analogies, it can really help you think through some of the aspects of various problems. And to that end, we'll finish with example 16 since it is here. So we have a man standing halfway between the center and one edge of a rotating plank. So some sort of a board like this. It's going to rotate about a certain point. And here's our person. Our question here is, if he wants to slow down the rotational speed, should he walk towards the center or the outer edge? Well, if we say momentum is conserved here, oh, you're welcome, Sam and Christian. My pleasure. Best of luck on the exam when you choose to write. But if this angular momentum is constant, then notice we can get the system to slow down if we can increase that rotational inertia. And we can do that by making the mass get farther away from the point of rotation, which means the answer to our question is we want our person to go to the edge of the plank. That'll get I bigger, and that'll make the system slow down. So we are at our time now. We're at our 1 hour in. So let me just finish off by saying, fantastic job, everyone, for investing your time, for being here. Thank you for that. And I say fantastic job because you're off to a great start already, thinking about how to prep for this test and getting yourself ready. Great resources to turn to for help as you prep include, of course, our Cracking the AP Physics 1 exam book. Also, College Board's past exams that you can access through their website. Great resource. You can see how questions were presented in the past and also how they were graded, which is a very valuable thing as well. If you want to prep with the Princeton Review a little bit more, we do offer tutoring options as well as some cram courses for your AP classes, including AP Physics 1. So you can go to PrincetonReview.com to look into that. And like I said, this is our third of 3 review sessions for AP Physics 1. You can find all 3 of these recordings on our Princeton Review YouTube channel. So again, thanks to everyone for being here and best of luck.